All right, hello. Today I'm going to try and answer a couple questions from our last video where we talked about how to measure the distance to the sun. Before we start, something of note is just I haven't prepared any script for this, and so I'm just going to be going off the top of my head. That might mean that I might pause occasionally and think about if there's anything I want to add, in which case I'll actually make an edit, a cut in the video, so that will be why. So I'm just going to write these questions down so we have them in one place. I might cut these out. So question 1. So the first question we're going to answer is, are the Earth, Sun, and Venus in the same plane? Or I think specifically, are we assuming this to be true? So the second question is, how do we measure theta m? And lastly, how do we know it's a 90-degree angle between our line of sight to Venus and Venus's line between itself and the sun? So let's get started with question 1. So how are we assuming that the Earth, Sun, and Venus are in the same plane? No. No, we're not assuming this. I'm saying that essentially this is included in our uncertainty in a couple of the measurements that we made. So specifically, there's an uncertainty in this distance here. So to recap, this is the distance arced out by Venus during the time between observer 1 and observer 2. So I think here we had it ended up being more than 10%. This is 20% here. This is a 20% error here. So I'm saying that this distance has an error that includes the fact that we might not be in a plane. So what I mean by this is, if you do this measurement over many years, what you will see is that some years when Venus comes by the sun, so here's the sun, what you'll see is that some years when Venus makes a transit by the sun, sometimes it's going to be on an upwards angle, sometimes it's going to be on a downwards angle, and sometimes it's going to come straight by. Now, we know that this inclination, because people have measured this, you can do it in exactly this method of just making this measurement a bunch of times, and eventually you'll find a maximal angle here, which will be about 3 degrees, I believe. That's just off the top of my head. And so, 3 degrees, what does that mean to a distance? So if we have a distance like this, where this angle is 3 degrees, and let's say that we wanted to measure this angle, which is 1, then if we were actually measuring this distance, this will give us, this is going to, rounding, give us 0.999. So this is a 1/100th error, which is much smaller than that 20% error that we're using. So we're not assuming they're in the same plane, and I have some pictures I can show for this in a second, but I am saying that they're quite close to each other, and that's something that I'm using by this observation. So number 2, how do we measure theta m? So this is a nice one. So you're going to have the sun in the sky here, and when we look out at the sky, what you're going to be able to find is Venus. And Venus is going to move back and forth along roughly something like this. So you'll notice it going back and forth, and it's going, if you make measurements of this angle, so when I say this angle, I mean, so if you take where Venus is and the sun is and you measure this angle, that's one measurement, and you just keep repeating this measurement, and you're going to have a table of measurements. So you're going to have like days, it's going to be like 1, 2, 3, up to, you know, maybe you'll do this for like a year, so like 365. And you have a table on the other side, and you have your angles, and so you'll measure things like 5 degrees, 10 degrees, you know, 45 degrees, 47, and then you're going to see it come back. It's going to go like 45 degrees, and then, you know, 30, and so on. And so you just chart these data points over a long time, and at some point you're going to see that one of these is a maximum, and so you'll take that one. You only have to do this over a single period, and you will have some maximum value. If you do this over many periods, you're going to be able to take multiple maximums and average them out. So that's how you can get theta max. The third one is, how do we know it's 90 degrees to the line of sight? So there's two ways to perhaps interpret this question, and I'll try and answer both. So the first is, how do we know this to just be true with a general circle? So let's do this. So it is a fact of a circle that at any point along its edge, if you draw a line from the center to that point, and then you draw the tangent line, this is going to be 90 degrees. That is a fact of circles. It is how, I don't want to say this. I was going to say this is how they are defined, but I think the more accurate description of how a circle is defined is the set of points that are all equidistant from the center. Yes, this is a poor explanation, all to say that it is because it is. It's just a fact of math. Probably the more interesting question, which I think is what you were actually asking before I gave you that poorly worded explanation, is these orbits are actually ellipsoid, and so how do we know it's actually pointing to the center? So let's put the sun a little off center here, and then, okay, continuing. So here is, I'm going to call this middle one Mercury's ellipsoid, and this outer one to be Earth's, a more circle, but also an ellipsoid technically. Okay, so to justify your concern, I've drawn a very disproportionate orbit than in reality. So my guess is that your concern is that if we have these very exaggerated ellipsoids, then what I was saying might not be true, because what I said is true for circles, right? That's how circles are defined. That's not how ellipsoids are defined. So to make the argument for you, if Earth is here at this point, then when I look for the maximal angles that Mercury can make from here, there's one point which is out here at, say, this point, and there's another tangent line at, say, about here. So your concern in this case is completely valid, in that, now let's do these in a slightly different color. this line and this line. So that's to say that this triangle here, this is certainly not 90 degrees. And this triangle over here, this is certainly not 90 degrees. So this is a valid concern. However, and I'll justify how we can check this in a second, these orbits, when we say that they're eccentric, are very, very close to a circle. And in so much that if I were to draw them to scale, I think you would have a hard time seeing, even by eye, that they aren't. So it might even be hard to tell, but I tried to draw these as almost circles, but not quite circles. So let's draw our planets. Here's one. So let's draw our tangent line there. So much nicer, right? And here. Okay. Okay, so I can't find out how to rotate this protractor, so we're just going to have to do some maths. How exciting. Yeah. So if we just take this side of the triangle, it looks like it's going from about 40 to 140. So I'm comfortable to call this 100 degrees. And this is then 80 degrees. So what do we have then? We want to know how much error is made by this thing reading 80 degrees and us assuming it's 90 in this greatly exaggerated case. So what we want is to have a triangle. Let's call this side to be 1 because we're going to want to scale it. This side and then this side, where this is our 80 degree side. And then what we want is to have another triangle where we're still going to call this 1. We're still going to have our angle. Remember, we never measure this length, right? We never measure this length. We don't know it. And then we have another one where we are saying this is 90 degrees, right? But this angle here, these angles are the same. And this is 90. So how much of a variation do we get in this? X, let's call this X prime. How much variation is there in delta X equal to X minus X prime, where this is a function of theta? So 1 second, and I will make a plot for you. All right, so I've coded this for you to hopefully give an example. The first side length here, we have X, we have side angle and angle, so we're going to use sine law to get that. So it's going to be the sine of this new angle, theta, divided by the sine of our erroneous angle of 80. For the blue triangle, it is just regular sine law, like sine, the trig function, right? Our delta x is the difference in these x values, and then we're going to plot this delta for varying values of theta. And when we do this, we see it looks like it's, I would call this a 100th error, 1% error, right? So this is with, again, this is a very exaggerated angle. We're getting about 1% error. So before, when we were doing this calculation and we were finding the distance x, I think we were calling there to be a 5% error on this, and then we were finding x to be about a 10% error. So the error that we can attribute reasonably, within reason of what we see, is about 1% error for a very exaggerated ellipsoid, and in our calculations we're using 10% error. So I would say this is very reasonable. Okay, so I think these roughly answer your questions. However, there's some more things I wanted to go over. And I'm going to cut now. Ooh, magic. Okay, so what I've done is I've just wrote a bit of code here, which is going to simulate some orbits for us. Yay. So here is some code we have. I'm going to have to slow this down, otherwise it's going to go really fast. So to scale, I have put Earth and Venus orbiting the sun. From the point of view of the blue line, this middle plot here is showing how it's going to move in the sky relative to the sun, which I have here at 0, 0. I didn't bother to include negative angles. It's just kind of easier to take absolute angles between things, which is why it's just bouncing when it hits 0, but whatever. I'm sure you understand this. So this is a bit towards your point 2. So each of these steps it's taking is a day. So what you do is each day you look at the sun, you look at Venus, and you are going to measure this angle here, right? The reason this is a little above is because I think I include about a 4-degree angle, maybe a 5-degree angle, just to exaggerate a bit. And so, of course, this angle that we're measuring is a little bit more than if it was, in fact, on a flat plane, like we mentioned here. So each day you're going to measure this angle, and then you're going to record it. So let me go back to the start here even. So on the first day, you have this measurement, and you go and you record it, and here it looks like I'm recording it to be probably about 1 degree. So there's a 1 degree difference, and then you do another day, and this looks like it's maybe 2 degrees, right? It's going out a bit. You do another day, it's going farther. Now we're at like maybe 5 degrees, and so on and so on and so on. You keep doing this iterative process, and you're going to tabulate a list of data points, right? That's what we're doing here. Okay, so you go through this process, and as it goes on, you're going to find that it's going to plateau. And this plateau is the fact that it's reaching the maximum angle. So you can see here in that bottom plot, it's leveling out, leveling out, leveling out, and there. I would say we've hit our max. So this is the maximum angle that I'm talking about. And it's hard to get a top view. Can we do this? So here's our top view, and this is roughly that 45 degrees I was talking about. So maybe I can even paste it here. So this is the 45-degree angle I was talking about, or the 47 or whatever. So this angle here, this is the day where you measure it to be around 47 degrees. And then you can just keep doing this, in fact. So you can make this slower, and you keep making these records. So you keep making these records, and you keep making these records, and you keep making these records. And you're going to record a number of these theta max values. And there's a nice benefit to this, which I realize is another thing that you can measure in your own backyard. What I want you to do is, instead of just doing this for like a year or until you find a single max value, maybe do this for like 1,000 days. Doesn't have to be just you, but you and a collection of people. Right, so this other experiment you can do is, instead of doing 1,000 days, which is like 3 years of recording, do this for much longer. You and a bunch of friends, you can take turns doing this. And so maybe you have 10,000 days. And why is this nice? It's because you can actually measure a really cool thing, which is, we were talking about my claim that these, although they're elliptical, they're very slightly elliptical. And so we can measure this. So right now I have plugged in A and B. You've if you've ever looked at how it, here, one second. Okay, so I have plugged in here the values A and B. If you've ever seen this before, it has to do with how we define ellipses. So A is the longer length and B is the shorter length. And then planets orbit around things at the focal point. So we have two focal points that it could orbit around, the other one's empty. And so it orbits around, say, the sun here, for instance. So I have these values of A and B. And let's exaggerate them here. It's going to freak out for a second while it redoes the calculation. Okay, so now I have a very exaggerated orbit. Let's put it in the top view. So now, now we're really seeing that it's a flattened out disk, right? So what does that mean? Looks like this is maybe a bit too high for how I've put my graph. So what this means is that if you make these measurements over the course of a long period of time, I'm going to zoom in on this graph a little, you're going to measure a lot of different theta maxes. And this is actually a good thing because it is giving you a tool to measure something else. So what this is letting us see is that over this period of time, we're getting all of these different measurements. And these are different by a lot, right? This is, this looks like it's 41 here, and we're seeing up to about 49. So this is about an 8-degree difference. It just so happens that this is close to my estimate. So, if you wanted, you could bump this error up to 8% even if you wanted. But it's about 8%. And what this is really cool is if you just actually record this, you'll be able to determine the eccentricity of Venus. This does require that Earth is a fully spherical orbit if you wanted to fit it to this data. However, you don't need to assume Earth is also spherical. You would just have to have another parameter in your model to fit to. So, for instance, though, which it is, Earth is very close. If you just record this for real and then you fit it to this model with varying A and B parameters, then you're going to be able to find what those A and B parameters are. And you're going to have a very high correlation because that's what they are. You're going to find them and it's going to be a very high correlation because they're moving in circular orbits. Right, okay. So when you put these back to their actual values, approximate actual values, what you'll see is that the variation now, it's still noticeable, and this is like a cool thing that you can measure, right? Now it's maybe closer to about 1 degree or 2 degrees maximum. So it's probably fair to say, actually, when I picked the uncertainties, maybe 5% is being very ambitious, Maybe in actuality, this should have been maybe probably 8 degrees in actuality. Yeah, this probably should have been higher. Okay, so to summarize, are Earth, Sun, Venus in the same plane? Is this an assumption we're making? No, we're not assuming that. It's something that when you go do this measurement, you can check yourself. You'll find that there's about a 3-degree difference between the planes, and that the 3-degree difference will give you a bit of variation. It's about 1%, but that variation is going to end up being less than the variation that comes from this third point, actually, that you made. 2, how do we measure theta m? I hope I described this well enough. Perhaps the video, the animation helps with that explanation also. And 3, how do we know it's 90 degrees to the line of sight? This is the most important objection. Obviously, if it's a circle, this is trivial. If it's absurdly elliptical, then this is a very good concern. But even if it's slightly elliptical, it's about 1%.